All right, so today we're going to be looking at section 1.4, which is over ratios and proportions. So the definition of a ratio and a rate. A ratio is a comparison of two numbers and can be written in three different ways. For example, the student to faculty ratio at a college is 40:1. We could just state it like that. We could also write it with a colon, or we can use it as a fraction as 40/1. Sometimes we'll see it like this, or like this. When the quantities being compared in the ratio have different units, it is called a rate. So when the units are different, like this one, it was still people to people. So this could have just been a ratio, but when the units are different, for example, the rate 30 miles per gallon is a comparison of two quantities, 30 miles and 1 gallon. It is perhaps easier to see this as a rate when it's written as a fraction, like 30 miles for every 1 gallon. Since the units, miles, and gallons are different, we refer to this ratio as a rate. So a rate is a type of ratio, and when it has different types of units, then we consider it to be a rate. For example 1, it says, find which of the following represent the rate 70 miles per hour. So we want it to still represent the same thing. So when I look at this first one, it's 70 miles for every 1 hour. So we have 70 miles for every 1 hour. It's just the same thing. So this one's good to go. This one's 70 miles every hour, same as per hour. This one is good to go. 17 miles in 15 minutes. Well, let's see if this would be the same thing. So think of 15 minutes. There are 4 sets of 15 minutes in an hour. So if I multiply that by 4, 17.5 times 4 will give us 70. So if we go 17.5 miles in 15 minutes, that's the same as 70 miles in 60 minutes, which is the same as 1 hour. So this one also checks out. 70 miles. Well, 70 miles per what or for every what. This one doesn't have enough information. It doesn't tell us anything else. For this one, 315 miles after 4.5 hours. If I take 315 and 4.5 and I divide those by 4.5 to get what it is for every 1 hour. So if we divide, we get 70 miles after 1 hour. So it's the same ratio or same rate. And F says 1 mile in 70 hours. So they switch the units. Now they just have 1 mile in every 70 hours. They can't just switch it like that on us. It would be a different rate. For applications of rates and ratios, it is common for recipes and mixtures to use the term part instead of a specific unit like cup or tablespoon. A part is any unit of volume, such as a teaspoon, cup, quart, or gallon. The person who creates the mixture can choose the unit based on the amount being mixed. For instance, if we're mixing for painting a wall, a part could be a quart. But if we're mixing paint for a canvas, a part might be just a 1-second squirt from a paint tube. So just depending on the context, we will use different sizes. Example 2 says a juice drink recipe calls for 3 parts orange juice and 2 parts pineapple juice. Below are several statements. Circle all that are correct. Part A says for every cup of pineapple juice, you need 1.5 cups of orange juice. Before I even start this problem, something that I like to do for it is kind of create like a key. Our key for the recipe, and I'll actually write it over here so we can use it even longer. Our key for the recipe is 3 parts of OJ, and I'm just going to simplify that or abbreviate it for orange juice, for every 2 parts pineapple juice. So I'll use PJ. So when we read these questions, I like us to compare it by comparing it to this ratio. This one, this example, is 1.5 of OJ for every 1 cup of PJ. If this creates an equivalent fraction with the key, then it will work. So we can check it out. To change it to be 2 of the pineapple juice, I could just multiply by 2. To change it from 1 to 2 of the pineapple juice, I would multiply it by 2. So if I double the OJ, that's 3 OJ. So as long as I double both, it gives me the same one. So this matches the recipe. For part B, it says, for every 2 quarts of pineapple juice, you need 6 quarts of orange juice. So for this one, it says 6 of OJ for 2 pineapple juice. If I simplify that fraction and I want to change it to our key, when I look at this, it's already 2 pineapple juice. So I can't change it to this. It's never going to end up being that same ratio. So this will not end up being equivalent with 3 OJ for every 2 PJ. So this one does not work. For C, it says when juices are mixed together, the mixture is 3/5 orange juice. All right, whenever it uses a fraction like this, I like to think of it as parts of a whole. So the entire thing is 5 parts. 3 of the parts are OJ. So it says 3 parts are OJ. So that means that the 2 parts that are remaining would be pineapple juice. And when I think of if that is 3 parts OJ for every 2 parts pineapple juice, it is. This one checks out. For D, it says the ratio of pineapple juice to orange juice is 2 to 3. So this was in a different order. If we read it, it was pineapple juice to orange juice. They just switched the order. And as long as they switched the 2 and the 3 as well, then this one also checks out. So this one, since they switched the order for both the words and the numbers, it is good to go. For E, it says if you have 15 ounces of orange juice, you need to add 10 ounces of pineapple juice. So we've got 15 OJ for every 10 PJ. Let's see if this can become an equivalent fraction with our key. So if we change it to 3 OJ, that would be to go to 15 to 3, I would divide by 5. If I divide by 5 on the bottom, I get 2 pineapple juice. Well, that matches my key. So this one also works. For F, it says if you use 4 cups pineapple juice, you can make 6 cups of the drink. So this one is really similar to C. I like to think of it in terms of parts. So we've got 4 cups of pineapple juice out of 6 total cups. That only leaves 2 for OJ. Well, we've never, in this whole thing, never had it be more PJ than OJ to make it match the key. So this one does not work. There are many instances in which we need to determine if ratios are equivalent. This can be done by simplifying the ratios or scaling one to see if it equals the other. So just like when we looked in section 1.2, we either want to multiply or divide the numerator and the denominator by the same number. Okay, looking at unit rates. A unit rate means a rate for one of something. We write this as a ratio with a denominator of 1. For example, if you ran 70 yards in 10 seconds, you ran an average of 7 yards in 1 second. Both the ratios 70 yards in 10 seconds and 7 yards in 1 second are rates, but the 7 yards in 1 second is a unit rate. So in order to change it to a unit rate, we just are going to take the first part of the rate divided by the second part. So this says Maddie lost 8 pounds in 10 weeks. Find her rate of pounds lost per week. So to change it to a unit rate, I'm going to take the 8 pounds for every 10 weeks, and I'm just going to divide. Whatever my answer is when I divide will be what it is for what she lost in pounds per week. So 8 divided by 10, I just get 0.8. A chef uses 9 pounds of sugar in 4 weeks. So we have 9 pounds for every 4 weeks. So we will divide. So 9 divided by 4, we get 2.25, and we're just going to write it, and this one would actually just still be pounds per week. Okay, looking at example 4, it says create a rate that compares suggested saturated fat grams to total calories for a 2,000 calorie diet. So when we look at our nutrition label here, the 2,000 calorie diet is just right here. If we look at what it is for the saturated fat grams, I'm going to look at this row right here, and it is 20 grams of saturated fat. So we're going to have 20 grams of saturated fat for every 2,000 calories. Now, what you can do in your calculator is you can just put 20 over 2,000, and you can just simplify that. So just take 20 over 2,000, and we get 1 over 100. So it's going to be 1 gram of saturated fat for every 100 calories. For part B, it says create a rate that compares the suggested saturated fat grams to total calories for a 2,500 calorie diet. So if we look at our 2,500 calorie diet, and then I look at what it is for saturated fat, it is 25 grams. So I'm going to have 25 grams for every 2,000 calories. So that's just going to be 25 over, 2,500. 2,500. If we simplify that, we again get 1 gram of saturated fat for every 100 calories. If we look at part C, it says compare your answers to the previous 2 questions. What do you notice? Well, the simplified versions are the same. So then what we can conclude about our simplified rates is that we will eat 1 gram of saturated, or the recommended amount is to eat 1 gram of saturated fat for every 100 calories we eat. So it's recommended to eat 1 gram of saturated fat for every 100 calories eaten. So in conclusion, since the comparison of suggested saturated fat calories to total calories is the same for each diet, we can say that the numbers of saturated fat grams and the number of total calories are proportional. So that's going to be just a key word to use. It is proportional. That is, they form the same ratio in each diet. So when 2 ratios are equal, they form a proportion. When 2 ratios are equal, the quantities are in proportion or proportional. So you can think of it as either way. For example, the rates 1 man for every 5 women and 3 men for every 15 women are equal to each other. So these are proportional or in proportion. Notice that a specific ratio is maintained. The number of women is always 5 times the number of men. Another perspective is that when the number of men is tripled, so is the number of women. Sometimes one ratio can be turned into another simply by scaling it, which we looked at section 1.2. To scale a ratio, you'll multiply or divide by the same non-zero number. If you can scale one ratio and turn it into the other, then we know that these ratios are equivalent. Okay, our last example, example 5, we have assume your teacher assigned a 5-paragraph, 750-word paper early in the semester that took you 2.5 hours to write. If the final paper of the semester must be 3,000 words long, how much time should you estimate it will take? Can you complete it in one day if you have procrastinated? Okay, for step 1, this breaks it down for us. It says, write a ratio that represents the number of words per hour you can write. So, if we know that we did 750 words, and we did it in 2.5 hours, we can find a unit rate by just dividing. So if we just divide, we will get how many words per hour we write. So I'm going to take 750 divided by 2.5. So I get 300 words per hour. Then it says to scale the ratio by a factor that makes both the numerator and denominator whole numbers. So for this one, I think it's actually okay if we just leave it as 300 words per hour. And so we can even just write it as a fraction. So we can say 300 words for every 1 hour. For step 3, it says now scale the ratio again to get it to the desired number of words in the denominator. So in the second scenario, when we are writing the final paper of the semester, it's 3,000 words long. So we want that top number, the numerator, to be 3,000 words. So I need to think of what will I do to scale this to 3,000. So it's an extra 0, so that means that we can multiply by 10. And if I do that to the top, I have to do it to the bottom. So I'm going to have 10 hours for the bottom. All right, so it's going to take you 10 hours to write the 3,000-word essay. So looking at our final answer, it says, so how long should it take to complete the 3,000-word paper? It would be 10 hours. And it says, can you complete it in one day? Technically, yes. But maybe not realistic. To actually sit down and have 10 hours to do it, or even have the stamina to do it for 10 hours straight, that might be a lot to ask. So notice that we can confirm this, that the starting ratio and final ratio are equivalent by dividing each of them so that they're the same number of words per minute. If we took 3,000 divided by 10, we would still get 300 words for every hour. Okay, this sums up section 1.4. If you have questions, please let me know.